Hey guys, this is going to be video number 2 for the Notes PowerPoints. This one's talking about equilibrium constants. I have an external microphone this time, so I'm hoping that the sound quality is better. It sounded better when I tested it. I apologize for the crappy sound quality of my first video, but let's move on. So last time I was talking to you about reaction rates and just generic equilibrium ideas. This time we're actually going to get into how we're going to do the math of equilibrium, which I know all of you are super excited for. So the first thing that I want to talk about with you guys is this thing called KEQ, or an equilibrium constant. You will see this represented a few different ways. I'm going to say KEQ a lot. Some people will also just say K, or even K sub C will be something that you might see, especially on the Khan Academy videos. I believe they use K sub C. But all of those things mean the same thing. It's KEQ, equilibrium constant. What it is the ratio of the product concentrations to the reaction concentrations. So once again, concentration is expressed in molarity, or moles per liter. So when I'm asking you to write these equilibrium expressions, as we're going to practice in a little bit, what I'm asking you to do is I'm asking you to write expressions with their molarities. So each one of those concentrations as we go is going to be raised to the power of the number of moles in the balanced equation. So what you need to remember from all the way back in first semester is when we were balancing equations, and that each of those coefficients that we were putting in front of the reactants and the products, those really are talking about how many moles are present in those equations. So here we have a really super generic sample reaction. We have A and B in equilibrium reacting to produce C and D. These lowercase ones, these lowercase things in front, those are the coefficients. So we're saying here A and B are reacting. Well, there's lowercase a moles of this, there's lowercase b moles of that, lowercase c moles of this, and lowercase d moles of that. So really what I'm just doing is I'm giving you a generic sample reaction so that we can make an expression that you could use as a template for later. So our KEQ equation is saying products, that's C and D in this equation, C and D are our products, C is raised to the power of its coefficient. So you see this tiny c right here, that is this tiny c right here. This lowercase d right there is that lowercase d here. Divided by, down here, we have our reactants. So really this is products over reactants, and that's something that you do need to keep in mind. But again, A is raised to the little lowercase a, which you see here, and B is raised to the power of the lowercase b, which you'll see there. And when we write these expressions later, you will actually be using numbers for these things. What does KEQ tell us? Why do we care? Well, the value is going to tell us whether the reactants or the products are favored in any particular equation. And what that means is if you have a really big KEQ, if you have a KEQ that's greater than 1, that means that the reaction is favoring the products, meaning that the forward reaction is easier and therefore a lot of product is going to form. If you have a KEQ that is less than 1, it means that the reactant side is favored, or the backwards reaction is easier, and therefore at equilibrium you're going to end up with more reactants than you have products. Because something that I talked about in my previous video that maybe you caught, maybe you didn't, was just because something's at equilibrium, that doesn't mean there's an equal amount of product and an equal amount of reactant. All that it means is that the rate of change of product to reactant or reactant to product has stabilized. It doesn't mean that there's an equal concentration on both sides. So once again, KEQ's bigger than 1 means there's more product at equilibrium. KEQ's less than 1 means that there's more reactants at equilibrium. Something that you do need to note is this little bullet point right here. Pure solids and pure liquids, like water, for example, water is the most popular one that we're going to see. You don't include those in the equilibrium expression. You don't. And for water, it actually kind of makes sense as to why, because if you're performing a reaction in solution, water's going to be there regardless. So you don't count it as something that's changing concentration over time, because the reaction is taking place in water anyway. So you're going to have water regardless. So we just leave that out of the expression entirely. Okay. So this is our first sample problem, and this is something that you're going to see a lot. You're going to see walls of text, and I know you guys love those. But this problem says the colorless gas dinitrogen tetroxide and the dark brown gas nitrogen dioxide exist in equilibrium with each other. So this first sentence, all that's telling you is, hey, guess what? Here's your chemical equation. We have our dinitrogen tetroxide over here in the gaseous state in equilibrium with this double-pronged arrow with 2 moles, that's what this number 2 means, the 2 moles of nitrogen dioxide, again in a gaseous state. So this first part told you what reaction was happening. Then we really get to the meat, the stuff that we care about down here. A liter of a gas mixture at equilibrium at 10 degrees Celsius contains 0.0045 moles of dinitrogen tetroxide. So we have 0.0045 moles of this guy right here. And we have 0.030 moles of NO2, or nitrogen dioxide. So we have 0.030 moles of this guy. And I want you to write the expression for the equilibrium constant and calculate the equilibrium constant, or KEQ, for that reaction. So if we go down a slide, here's our equation once again, copied that down here. Our equilibrium expression is going to look like this. Can't really highlight it very well, but it looks like this because, again, your equilibrium expression is written products over reactants. NO2 is your product here, and reactant, so there's only one in this case, that's your dinitrogen tetroxide, and that goes down here. So when you see these little brackets here, these brackets in chemistry represent concentration. So if you ever see anything inside of brackets, I'm telling you, hey, that's a concentration. So we're saying the concentration of nitrogen dioxide raised to the power of 2, and that 2 comes directly from your equation here. That's where this 2 is coming from. Divided by your concentration of dinitrogen tetroxide, and there is no exponent right here because you do not have a coefficient up here. You could put an implied 1 there if it made you feel better. You could raise it to the power of 1, but if you've been paying attention in math at all, you know that that doesn't really do anything. Raising something to the power of 1 does not change it. So this entire thing here is your equilibrium expression, which is basically the roadmap for how you're going to set up your actual problem. So if I ask for an equilibrium expression, I'm asking for this. When you solve this problem, though, is where you're going to start filling in numbers for that. So if we recall from the previous slide, this 0.030 moles per liter, or molarity, that was the concentration of NO2 at equilibrium. And if you want to switch back to the previous slide, you can see that. So again, that's raised to the power of 2, just like in my equilibrium expression. 0.0045 moles per liter molarity, that was the concentration of my reactant at equilibrium, or my dinitrogen tetroxide. And again, that's not raised to any power because we don't have one in our equilibrium expression. So if you solve this out, if you take 0.030, square it, and then divide it by 0.0045, you get approximately 0.2. That is a KEQ, and we can use that to determine whether or not the products are favored or the reactants are favored. So this is a KEQ that is less than 1, which really is telling you that that your products are not favored in this case, because if it was greater than 1, then your products would be favored, but since this KEQ is less than 1, it means that your reactants are actually favored in this case. So here's sample problem number 2, which again, we've got this entire wall of text, and I don't want you to get freaked out by the giant wall of text, because so many of you just look at that and you immediately check out and you're like, oh my god, Miss Seiler, I can't do this. This is horrible. And then I sit down with you and we walk through it together and suddenly it makes sense. But you guys have the capability of doing this on your own. I'm not like a magic witch with like all-seeing powers. It's just that I break down problems step by step as I go so that I don't get intimidated by giant walls of text. So we have this first sentence: bromine monochloride, BrCl, decomposes to form bromine gas and chlorine gas according to this equation. So again, we see our first sentence telling us what is going on, telling us this equation, because I could theoretically ask you to write this equation based on a sentence like this. But in the sample problem, it is written for you, and hey, guess what? It is also balanced for you. So we have our bromine monochloride gas here. We have 2 moles of that. That's what this 2 represents. In equilibrium, reacting to form bromine gas and chlorine gas. If we remember, bromine and chlorine are both diatomic elements. Do not forget about those. So now we have what we care about. At a certain temperature, the equilibrium constant is 11.1. So in this case, I'm telling you what KEQ is already. And it says, suppose that pure BrCl is placed in a 1-liter container and allowed to come to equilibrium, resulting in 4 moles of Cl2. How many moles of Br2 and BrCl are also present in the reaction mixture? So suddenly now our problem is asking us for something completely different. And immediately I know some of you are like, what? I don't understand what's going on. That's okay. But you have all the information that you need to solve this problem here in this wall of text. All you have to do is break it apart. So going here, once again, here is our reaction that's actually taking place and it's balanced. According to your equation, when BrCl decomposes, equal numbers of moles of bromine and chlorine are formed. And you know that because there is no coefficient here and there is no coefficient there, which means that 1 mole of this is forming and 1 mole of that is forming, if we recall the implied 1. So when I say that Cl2 is forming, and if we go back here, I did tell you 4 moles of Cl2 formed, and I also told you this was taking place in a 1-liter container. So your concentration of Cl2 is given to you, 4 moles in every 1 liter. And so if you know that 4 moles of Cl2 is forming when Cl2 and Br2 are in a 1-to-1 ratio, it also means that 4 moles of Br2 formed as well, meaning that that concentration is 4 moles per liter. So we can see that down here when we're looking at our equilibrium expression. So just backtrack for a second with me. To set up our generic equilibrium expression, KEQ equals products over reactants. And we see our concentration of Br2 times Cl2. Again, there is no exponent because there's no coefficients up here. Divided by our reactants, in this case, again, there's only 1, our concentration of BrCl raised to the power of 2 because there is a 2 right up there. And then once we have this, we can start filling in numbers. So here we have our 4 moles per liter of Cl2 and Br2, which again, I just talked you through how you knew that these were the concentrations, divided by our unknown, divided by our concentration of BrCl raised to the power of 2. Now, this 11.1 also comes directly from the problem. So if we switch back a slide for a second,